Okay, we are basically going to use the second form. If you write down that equation, you're good, but when you see it on the formula sheet, chances are you're going to see it like this with these absolute values, and instead of the k, they might actually put this in instead, but you're going to think this the whole entire time. So the force between the two charged objects can either be attractive, like that example that I showed you up above when the objects are oppositely charged, or the forces can be repulsive if the charges are the same, right? So if the charges are alike, they're going to be repulsive. Two positive charges repel each other, two negative charges repel each other. But if they are not like each other, then it's going to be like up here, and they're going to be attracted to each other because opposites attract. So let's get into our example. Oh, this last part here. If you ever have they talk about, I don't know, make a motorcycle lost an electron, right? A motorcycle is this big, huge thing. You're going to act like it's a point charge, which basically means it doesn't matter if this is the object that they're talking about and it has gained an electron. You're going to say, okay, this whole entire object is negative. Instead of thinking about this whole big crazy object that has this negative charge, you're just going to think there's this tiny little point in space that has a negative charge, right? You're thinking of it as a point that has a charge. Okay, let's do two examples that are very similar to your homework. And in your homework, I'd actually do number one. I'd skip two and three. I'd kind of do like four and five, and then probably come back to two and three, and then six. That's just, I think, one and probably four are the easier out of the ones, out of the problems. Anyway, so 2 point charges are 5 meters apart, right? This is our R value, right? It's in meters. We know that's a distance. If the charges are 0.02 coulombs, that's one of our charge, so we can call that Q1, and 0.03 coulombs, so we're going to call that Q2. What is the force between them, and is it attractive or repulsive? Well, they don't say if it's positive or negative, but because they didn't put like a negative in front of the charge, we are assuming that just like any number that we see, because it's not designated as negative and the statement didn't say they're negative, we're assuming that they're positive. So using Coulomb's law, right, our electrostatic force that's either going to attract or repel is equal to our constant K times Q1 times Q2 all over R. And remember, you have to square that value. A lot of times students forget that. Each time, make sure you write out your equation as always. So K is our constant, 9 times 10 to the ninth. Our charges are in coulombs, so 0.02 and 0.03. Remember, even if they were negative, we would still put them in there. We're kind of putting in the absolute values. Our distance has to be in meters, which it is, 5 meters, so 5 squared. And when you punch that in your calculator, your 9 times 10 to the ninth times 0.02 times 0.03 divided by that 5, and make sure you square it, you get 216,000 newtons. Or you could write it as 2.16 times 10 to the fifth newtons. Doesn't really matter. You don't have to put it in scientific notation, right? But either of those would work. Now, remember that we assumed both of these charges were positive, and so because of that, the force is repulsive, right? Because both are positive. So think that basically that you have these charges that are both positive, and because of that, they are going to repel each other. So if we asked like, hey, what's the charge on that 0.03 Coulomb charge, we could say, well, it's 216,000 newtons to the right. Or if it was this other Q1 charge, well, we'd say it's negative 2,016 newtons, or 216,000 newtons, and we would say that that force is to the left for that one. So that problem is about as easy as it's going to get as far as number one goes. Now, looking at this equation, hopefully you can see, like, when it asks you, then all of a sudden part B is going to say, hey, what happens if you double the charge? Well, looking at that equation, our electrostatic force is proportional to the charge. So if you doubled any of those charges, it would double the force. If a charge got cut into a third, then the force of repulsion would be cut into a third. And they'll also change that distance on you. Remember, it's that inverse square law. So if they said they doubled the distance, we'd say, okay, well, 1 over, we doubled the distance squared, so that's 1/4, so my force is 1/4, right? Or let's say they cut the distance in thirds, so 1 over, my R is now 1/3 of what it was before, squared, which basically means it's 9 times the force, right? 1/3 squared is 1/9. Then I'd have to simplify that fraction of 1 over 1/9, which would become 9, and I can say, okay, well, my force is 9 times greater. That'll kind of be like the point B and C in your problems. Last example for this video, a group of 2 protons, right? So we have a point charge that we're thinking of is 2 protons. And we know that 1 proton, right? 1 proton is 1.6 times 10 to the negative 19th, which means these 2 protons are 3.2 times 10 to the negative 19th coulombs. Now it says that the 2 protons are 5 millimeters to the left of a group of 3 electrons. So my distance between them is 0.005 meters, right? We have to be in that distance, and then our other point charge is made up of 3 positive charges, and if an electron is negative 1.6 times 10 to the negative 19th, then if there's 3 of them, let me fix this real quick, thinking that there is 3 electrons, right? Those are negatively charged. Then that would be 4.8 times 10 to the negative 19th, right? Because 1.6 times 10 to the negative 19th times 3, because there's 3 electrons, is 4.8 times 10 to the negative 19th. Now, they might also say something like, well, you have an atom that has lost 2 electrons. So let's say we have atom X, and it lost 2 electrons. That means it has a +2 charge, or it has 2 more protons than it has electrons, which means it has a charge of positive 3.2 times 10 to the negative 19th, right? Or if you have something that says these 3 electrons, let's say your other element, Y, has gained 3 electrons. It has a charge of -3. That's the same thing as saying it has a charge of negative 4.8 times 10 to the negative 19th. So we want to figure out the magnitude and direction of the force acting on the electrons. Well, we know that these electrons are attracted to the protons, and so this really is the force we're talking about. What's the force on the electrons? Now, when we put those values in our KQ1, Q2 over R squared, it's telling us the absolute value of this force and the absolute value of this force, but all they ask about is the magnitude and direction. Oh, sorry, A is asking the magnitude and direction acting on the protons. So that's going to be this force, right? Let's say we'll say force P for proton and force E for electron. They're going to be the exact same number, they're just different directions, right? The force proton is to the right, the force electrons is going to be to the left. So we punch in our numbers, 9 times 10 to the ninth. Our charges of our two protons, 3.2 times 10 to the negative 19th. Our electrons, remember we're doing absolute value here, so 4.8 times 10 to the negative 19th over our distance in meters, 0.005, and make sure you square it. So you're going to get that the force of the proton is positive or to the right, right? And that comes out to be 5.53 times 10 to the negative 23rd newtons, right? All forces are newtons, which means the force on the electron is negative or to the left at 5.53 times 10 to the negative 23rd. That should get you through homework 1.